Hey guys, welcome back to Stonks Maxxing Day 73. This is actually part 7 of Intel, but I think what I want to do for this stream is watch some videos on branch education. So there's some cool things that they have here, how are microchips made, and then also how does computer memory work. I think for learning about the background of Intel, it would be helpful to understand, maybe at a high level, the process of how these microchips are made. So I think this is where, to start off the stream, I might do a little bit of learning, like the actual technical learning behind it. Okay, this is actually pretty cool. So I gotta, yeah, that's nice. I gotta take a look at some of these places. Yeah, I'm glad I wrote all these notes because I'm looking back and I totally forgot I had all this stuff. Selling to businesses, selling to everyday people. Okay, that's cool. Let's see. Do I have anything else here? Sectors. Structure? Okay. Then yeah, I'll probably create a new, what's this? Okay, so I'll create something new here, and we'll call this, oh, totally forgot I had that. Call this semis. Heading 1, semiconductor, manufacturing, branch education. Okay. Alright, I don't know if you guys can hear this because I have my headphones in, but let's full send it, see what we can do.
Just where I'm at in life, like the people who are closest to me inspire me.
The size of a tiny ant? Well, inside the smartphone are 62 microchips containing a total of 90 billion transistors. These microchips are incredibly powerful, and the corner...
Okay, so let's maybe define some key vocab to start, right? So what's a transistor? I think at a high level, it's really just a switch to turn something on or off. In this case, that something is an electrical current or an electrical signal. Okay. So, let's see, what is a processor, right? This is a type of device that is composed of transistors. Can perform mathematical calculations, right? I think that's essentially, let's maybe make it can execute instructions. I think that's a better way of saying this. And then, let's see, what else? What is a chip? Right, so this is really just a piece of silicon wafer that is chipped off to form a processor. Yeah.
Cornerstone of all textures. These
Okay, so it seems like inside, cool facts, right? A smartphone, 60 billion transistors. I mean, that's a shit ton of transistors.
microchips are incredibly powerful and the cornerstone of all technology. But how are billions of nanoscopic transistors manufactured into a microchip the size of a tiny ant? Well, all these microchips were manufactured in a semiconductor fabrication plant like this one. Inside it is a clean room. Conductor fabrication plant like this one. Inside it is a clean room which spans the area of 8 football fields.
Shoot. Okay.
Is a clean room.
So a fab. So this is the place semiconductors are made. Alright, let's start then with the fab. Fab. Semi-fab is composed of the following. So we have a clean room,
which spans the area of 8 football fields.
spans the area of 8 football fields, right? So a football field is what, 100 yards? So if you have, and I guess, I don't know what the square footage is, right? 100 yards, so that's the kind of length of the rectangle, but the width, maybe 10. So it's like 1,000 yards, square yards. So if you have 8, then you have 8,000 square yards.
Fields and is filled with hundreds of machines ranging in size from that of a van to that of a city bus. Machines ranging in size from that of a van to that of a city bus.
Okay. So let's see, the clean room. Things that falling exist in clean room. So you have chemical, mechanical. I've never heard of this. Planner, extreme, ultraviolet, chemical, mechanical planners. Let's see, what is this? Okay, so I guess this is some type of chemistry type process. Yeah, I don't know. Is there a machine? Maybe. Okay, I guess this could be one. So that's about the size of a car. Extreme ultraviolence. Photography. EV photography machine. Jesus Christ, this is huge. I don't even know. What is this? Numerical aperture. ASML. High aperture. Machine. Twin scan. EXE. That's crazy. About 5,000.
And costing anywhere between a few million and 107.
So, let's see, 3.5 million price tag. Okay, so I guess how much? Question. Oh, okay, that's cool. All right, so how question? Oh, go ahead. How much does it cost to create a fab? Does it cost to maintain a fab? And then how long does it take to make a fab? What are the components of a fab? Right, so talking about the clean room right now. And then within this clean room, you have $3.5 million machines, and then you also have $170 million machines. So that's a lot of money.
$70 million. Within this microchip factory, silicon wafers travel from machine to machine and undergo around 1,000 processes over a 3-month period. And by the end of production, each silicon wafer will be a 3-month period and undergo around 1,000 processes.
Actual production of processors of microchips. Place a single silicon wafer will undergo 100 plus processes, chemical / physical processes before it has final microchip product. So 100 plus chemical physical processes, that's a lot.
Over a 3-month period and undergo around 1,000 processes over a 3-month period. And by the end of production, each silicon wafer will be covered in hundreds of CPU chips, each containing 26 billion transistors. CPU chip of production, each silicon.
Wow, we haven't even gone past the first minute of this. Let's make a little comment. So, branch education, how chips are made. Okay, yeah, I don't need the actual hour, so just a second.
Silicon wafer will be covered in hundreds of CPU chips, each containing 26 billion transistors. When we zoom in, we can see the nanoscopic transistors at the bottom and over a dozen layers of wires above. Billion transistors of CPU chips, each containing
single silicon wafer can contain hundreds, 100 plus microchips. Chip these days has 20 billion plus transistors. Okay.
26 billion transistors. When we zoom in, we can see the nanoscopic transistors at the bottom and over a dozen layers of wires above. This integrated circuit is then cut out from the wafer, tested, and packaged so that it can be installed into your desktop computer.
Okay. Maybe let's say actual key process breakdown. There are 3 key steps. So, wafer manufacturing, on wafer, and then I think we also have on a wafer processing a final processor, and then finally is packaging. Okay.
Tested and packaged so that it can be installed into your desktop computer. In this video, we're going to explore the entire microchip manufacturing process and show you how billions of nanoscopic transistors and an impossibly complex 3D maze of wires are manufactured in one of the world's most technologically advanced microchip factories.
You know, I wonder if there's one nearby. That would be very interesting to go to. The one in Virginia. Let's see. Nothing in Maryland. Virginia. Richmond. Shoot. Fab 6 micron. Manassas. Okay, so it's kind of far. I don't know if there's a metro station here. Yeah, there's not. Okay. George Mason's there. Okay, interesting. I didn't know that. All right.
It's an incredibly complicated process, so stick around and let's jump right in. A portion of this video is sponsored by Brilliant.org. There are two sides to understanding how microchip manufacturing works. The first is the sequence of steps and processes needed to build the nanoscopic transistors and the labyrinth of wires. Whereas the second is how the semiconductor fab and multi-million-dollar equipment of the clean room floor work. And we'll be flipping between these two sides of the second. Nanoscopic trans is the
Okay, so clean room. Key to understanding microchips work. Two key sides. So sequence of steps. Underpin the creation of microscopic transistors and wires that lay on top, and then how the machines and help with the process. Clean room.
sequence of steps and processes needed to build the nanoscopic transistors and the labyrinth of wires. Whereas the second is
Wait. See if we can make a comment. Add comments. Education.
is how the semiconductor fab and multi-million-dollar equipment of the clean room floor work. And we'll be flipping between these two sides to get a complete picture. Let's start by opening up this desktop computer, focusing on the CPU and taking a look at what's inside. Here we have an integrated circuit, or die, which we'll refer to as a chip. This chip has 24 cores, a memory controller, a graphics processor, and many.
Okay, this seems like Intel. I'm noticing a few familiar topics. Raptor Cove. Okay, let me see if I can increase resolution here. All right.
The other sections.
Okay. This is very helpful. CPI, the CPU. What CPU looks like under the hood is composed of multiple components, right? Integrated circuits, die, chip. Are used interchangeably to describe a piece of silicon transistors and wires, shown in the picture.
Within one of the cores, we can see its block diagram and the various elements. Zooming in on this multiply block, see its block diagram.
These are cores. Yes, there's, yeah. So I guess this is what happens. This is core. Looks like underneath the hood. Hood of a CPU.
And the various elements. Within one of the cores, we can see its block diagram and the various elements. Zooming in on this multiply block, we find a diagram.
These pictures are referred to as block diagrams. Okay. CPU core.
And the various elements. Zooming in on this multiply block, we find a layout of 44,000 transistors that physically execute 32-bit multiplication and constitute just 0.00017% of the overall 26 billion transistors in the CPU. Zooming in even further, we see layers of metal wires or interconnects, and at the very bottom are the transistors that form the basic logic gates. And at
FinFET transistors. Perspective size. Yeah, okay, this is a very.
we can see its block diagram and the
Above. Conduct operations. Around 44K transistors. So this will be 0.01% as a basis point. So this is half, not even half, a tenth of a basis point. I guess more so 15th, but
the various elements. Zooming in on this multiply block, we find a layout of 44,000 transistors that physically execute 32-bit multiplication and
32-bit multiplication. Right, so I guess if you have 64-bit, just double. I don't know exactly how that works, but I think you just increase the string of transistors that you have. I might need to move real quick. My computer's about to die. Oh shit. see if I can transport this. Yeah, this works. Okay. No, I might have not brought my charger. Oh, thank God. God bless. I did bring it. Oh, okay. Alright, so I've got it hooked up. Alright, so let's keep on chugging along.
Constitute just 0.00017%
Oh, shoot, I forgot a zero.
of the overall 26 billion transistors.
Oops, 26 billion.
Transistors in the CPU. Zooming in even further, we see layers of metal wires or interconnects, and at the very bottom are the layers of metal wires.
Okay. Maybe let's take a look at, should I say this? The base, call this base elements. There's basic to most basic / fundamental elements of a microchip are one interconnects microscopic wires. Guess what I mean by microscopic? It's like super small that you need a microscope to see it. And then what else is there? Transistor. Logic gate / switch.
Or interconnects, and at the very bottom are the transistors that form the basic logic gates. Note that these layers of metal interconnects aren't floating, but rather the empty space that you see is filled with insulating materials, thus providing structure and preventing the metal wire layers from touching. Thus providing space that you see is filled with insulating materials.
Okay, so it seems what this guy's saying is that there's also something else here. Gotta do some creative moving things around. Alright, but there is insulating material on the microchip that provides structure for the interconnects or the wire. So the wires, right? I think the goal here is this helps prevent the wires from touching each other, which I guess is a bad thing. I don't know too much about electrical engineering, but I'd imagine that if one wire crosses another, there might be unwanted relationships with the current. That's my best guess. Alright, let's keep
thus
going.
providing structure and preventing the metal wire layers from touching. Furthermore, here we're only showing the transistors at the bottom and 5 layers of metal interconnects, with vias traveling vertically between the layers. In actuality, there are a total of 17 metal layers of wires in the CPU, and each successive set of levels uses larger and larger interconnects. And there are a total of 7 transistors at the bottom and 5 layers of metal interconnects, with vias traveling vertically between the layers. In actuality, there are a total of 17 metal layers of wires in the CPU, and each successive set of levels uses larger and larger interconnects. At the bottom are local interconnects that move data around this 32-bit multiply circuit. In the middle are intermediate interconnects that move data around the core, and at the top are global interconnects that move data around the entire CPU. You might be wondering how small are these transistors? Zooming in again and past the interconnect layers, we find FinFETs, which are transistors whose channel dimensions are 36 entire CPU.
Okay, can I use the bathroom real quick? But I feel like this diagram is actually pretty interesting. So when you look at how data is transferred on a CPU, you have the idea of interconnects, right? So these are the wires. And it's kind of like how the highway system works in the US. You have local roads, you have local highways, I should say. So I think in the Maryland case, like Great Seneca Highway, you also have, let's say, state highways, so like I-270, and then you also have these global highways, or I guess national highways, so Route 66. And I think there's a very similar way of how data is transferred, or how a CPU is actually cooked up together. You have regional, local, I think local first, and then regional, and then global interconnect. Heading to CPU's interconnect highway system. Interconnects. Please to how the
at the bottom and 5 layers of metal interconnects, with vias traveling vertically between the layers. In actuality, there are a total of 17 metal layers of wires in the CPU, and each successive set of levels uses larger and larger interconnects. At the bottom are local interconnects uses larger and larger layers in the CPU, and each successive set of levels uses larger and larger in the CPU, and each successive set of levels.
Okay. So this is actually what kind of looks like a Minecraft tower of sorts. How many levels does a CPU? interconnect layers. Ooh, that's fire. Oops. Multiple layers of interconnect. The bottom close to transistor, top is far. Okay. Interconnects are layered on top of each other like a cake. The local interconnects, are wires that sit on top, very close to the base transistors on a CPU. They move data around locally in a predefined region, right?
Uses larger and larger interconnects. At the bottom are local interconnects that move data around this 32-bit multiply circuit. In the middle are intermediate interconnects that move data around the core, and at
Intermediate interconnects, wires that sit top of local interconnects that can move data around a larger region, a core, and then global interconnects, wires that sit on top of interconnects and move data around the entire chip.
the top are global interconnects that move data around the entire CPU. You might be wondering, data around this 32-bit multiply.
Branch education.
Circuit. In the middle are intermediate interconnects that move data around the core, and at the top are global interconnects that move data around the entire CPU. You might be wondering, how small are these transistors? Zooming in again and past the interconnect layers, we find FinFETs, which are transistors whose channel dimensions are 36 by 6 by 52 nanometers, with a transistor-to-transistor pitch of 57 nanometers. Clearly, the transistors are incredibly small. Here's a mitochondria, a dust particle, and a human hair for size comparisons.
Oh my God.
Now that you have a sense of what the transistors and 7 nanometers. Clearly, the transistors are incredibly small, of 52 nanometers.
This actually puts into perspective how small a single nanometer is. I didn't realize that the mitochondria was bigger than a transistor. How many transistors can I fit in the palm of my hand? That's a good question, actually. My hand.
That goes into it. This is the largest chip the world's ever seen. One of our computers, this is our latest generation, This is the chip
Oh,
that goes into it. This is the largest
you know,
chip the world's ever seen.
I just realized I can fit maybe multiple chips on my hand. So if I use the math of 26 billion transistors on a single chip, I think my hand can maybe hold, just eyeballing here, in the palm of my hand. So maybe like this region, like 6 or 7 chips. Let's simplify the math. 7 times 25. It's 175 billion transistors. Oh man, that's a lot.
This is beyond the limits of physics. We had to invent some new technology to make it possible to do this.
How many bits are in?
208 billion transistors.
In that?
Gosh, it's even hard to...
What we're looking at?
In this little tiny part in the middle.
And what should that cost?
This will cost, $30,000, $40,000.
And how much did you spend to develop?
The very first one, the R&D budget of this generation is probably something like $10 billion.
Jesus Christ. What? Okay, so I think the takeaway here is that this is nothing short of magic. The dark arts. Yeah. I think that might be actually. The dark arts. Okay, I did say I have to go use the bathroom, so I'll be back in a sec. Back. Okay, so maybe this is a good time to talk about transistors. Transistors, right? Transistors are essentially microscopic switches. A okay, and I think this goes back to the process technology. So when people say that, oh, TSMC has a 2 nanometer process technology, or 2 nanometer node. It's more of a misnomer because I don't think it's actually 2 nanometers, right? This right here is 36 nanometers. If you look at the width, if you look at, I don't know what this is, the height of the gate, yeah, that's 52 nanometers. So that's a lot more than 2. So I think that nanometer process technology is essentially marketing. It does refer to kind of like, I think, the chip count that you can include on, sorry, not the chip count, transistor count that you can include on a single chip. So I guess in this video, there's 26 billion. And in NVIDIA's, I guess what Jensen was holding, he was holding a H100, that's my best guess. So it has 100 or so billion transistors, which is, I think, the 2 nanometer node, because they're all made by TSMC. Alright. Flow through. Transistors, size of these transistors are only a few nanometers.
With a transistor to 36 by 6 by 52 nanometers, with a transistor to transistor pitch of 57 nanometers.
Okay, this is cool. So the transistor to transistor pitch is nanometers. So I guess the distance between covers 2 FinFET gates is around 57 nanometers. Okay, so what's a nanometer? I think a nanometer is 1 billionth of a meter, right? Billionth of a meter. That is crazy.
Clearly, the transistors are incredibly small. Here's a mitochondria, a dust particle. Transistors are incredibly small. Here's a mitochondria.
Size. Transistor versus powerhouse cell.
A dust particle, and a human hair for size comparisons. Now that you have a sense of what the transistors and labyrinth of metal interconnects look like, let's explore how they're manufactured. We'll begin with an analogy. Imagine baking a cake that's 80 layers tall, with each layer cut to a unique shape. To make this cake, there are 940 steps in the recipe, which takes 3 months to complete and includes hundreds of exotic ingredients. And if any measurement, baking time, or temperature is more than 1% off, then the cake is entirely ruined. That's kind of what it's like to make a microchip. But microchips are even more complicated. Let's look at a single layer of this integrated circuit and run through a simplified set of steps used to build it. To start, a layer of insulating silicon dioxide is deposited in the circuit, or kind.
So I gotta mentally prep for this because I think I'm about to go on this sort of spiritual journey of sorts into how to make microchips. But I think to start, this is a good analogy. Making a microchip, baking a cake. Cake.
Layers tall. Analogy. Imagine baking a cake that's 80 layers tall, with each layer cut to a unique shape.
So each layer is cut to a shape.
To make this cake, there are 940
steps.
40 steps in the recipe, which takes 3 months to complete and includes hundreds
of exotic ingredients. 3 months to complete any of the temperature or slightly messed up percent variance. The whole cake doesn't even work.
hundreds of exotic ingredients. And if any measurement, baking time, or temperature is more than 1% off, then the cake is entirely ruined. That's kind of what it's like to make a microchip. But microchips are even more complicated. Let's look at a single layer of this integrated circuit and run through a simplified set of steps used to build it. To start, a layer of insulating silicon dioxide is deposited on top of the wafer, and then a layer of light-sensitive photoresist is spread across the top. Next, using UV light and a stencil, a pattern is applied to the photoresist. Solvents then are used to remove the areas hit by the UV light, thus creating a patterned mask layer. Using the mask, the revealed silicon dioxide is etched away down to the previous layer. Next, the mask layer is removed, and a layer of copper is added to cover the wafer and fill in the areas that were just etched away. Finally, the surface is ground down and leveled off to reveal the copper and insulator patterns, and thus a single layer is completed. In order to build the next layer, which is a vertical set of metal vias, we repeat the same set of steps, but use a different pattern for the photomask. Since these layers are all built using the same set of steps, it's more effective to visualize the steps as a circle, like a clock. To build all the 80 layers of the die, this sequence is repeated over and over, resulting in 940 steps. One important note is that the FinFET transistors at the bottom are even more complicated than the metal wires, and thus additional steps are needed to fabricate them. Furthermore, cleaning the wafer to wash away dust particles that may have landed on the wafer, as well as inspecting the wafer to make sure everything is being built properly.
This is so crazy. I'm looking at this and my head is spinning.
Happens frequently, and these steps need to be added to the circle. A different tool is used to complete each of these process steps. Now that we have an understanding of the steps, let's take a look at this semiconductor fabrication plant.
Okay, I'm gonna actually.
The resist is spread on top of the wafer. Apply down 3 layers of the.
Let's try to summarize what this guy said. Call this the level noob. So this is the new version. Very high level there. 1, 2, 3, 4, 5, 6. Okay, there are 8 key steps to make microchip. I guess this is the interconnect part, right? So, side position, photo resist, spin code, photo lithography, etching, photo removal, metal deposition, okay, form a cycle.
Separate visits to the lithography tool. We could spend another hour talking about photolithography, but let's move on to the next category of tools. Deposition tools are used to add or deposit material onto the wafer. A lot of times we use the mask layer from the photolithography step, top of the wafer, and the insulated set of steps used to build it. To start, a layer of insulating silicon.
Okay, so call this branch education 0549. Alright, that's good. Okay, so the first step, right? Oxide deposition. Okay, so what the fuck does oxide be, and what does deposition? Oxide deposition. I guess this is like some sort of chemical reaction with oxygen, right? Okay. Chemical compound containing at least one oxygen atom. Okay. Or not atom, but element. Okay. Deposition. Wait, are elements atoms? From one type of atom. Yeah. guess the act of positing something, putting something in another thing. I don't know, that sounds kind of wrong. So, I mean, using context clues, you're putting oxygen. So with this in mind, these two terms, find the step is essentially spraying, depositing layer of oxides onto an interconnect layer.
Silicon dioxide is deposited. To start, a layer of insulating silicon dioxide.
Silicon.
Build it. To start, a layer of insulating silicon dioxide is
Dioxide. Wait, what is dioxide? Oh. Shit. This is why I gotta study chemistry again. So I didn't realize that dioxide, carbon dioxide, one carbon, two oxygens, an oxygen. So a dioxide is a chemical compound with two oxygen elements. Okay, yeah, CO2. Yeah, that makes sense. That makes sense. Totally forgot about that.
is deposited on top of the wafer, and then a layer of light-sensitive photoresist is spread across top of the wafer, and then a
What does this do? Okay, so I think the next step then is photoresist spin coat. So what is photoresist? Oh my god, this sounds so complicated. What the hell is a polymeric material transfer micro and not nanoscale patterns to a substrate through radiation-induced solid? Oh my god. So substrate, I think, is like the underneath, the underlying material. Oh, okay, this is actually cool. So I guess you could somehow destroy, I don't know exactly what this is doing, but you can modify the photoresist using light. Cool. Okay. This is actually very helpful. Organic materials that molded with white, right? Caption this real quick. Posing step 2. And the photoresist layer.
Insulating silicon dioxide is deposited on top of the wafer, and then a layer of light-sensitive photoresist is spread across the top. Next, using UV photoresist is spread.
Okay. Step just coats layer with prep for the next okay. So yeah, so this, I guess, step 2 is more so of a preparation for photolithography. So I think litho means with lights. Photo, no, what photo actually means, like picture. It's like drawing with light. Photo equal to breaking down the components of this word. Okay. Breaking down what those Greek for graph for so photography drawing with lights photo. Yeah, what does litho mean? So litho mean stone. Okay, I don't know if that's right. In photolithography. Oh shit, it is. So it is stone. Okay, shit. So stone. So stone drawing on the plate. Yeah, I don't know. With white stone, like Minecraft.
Across the top. Next, using UV light and a stencil, a pattern is applied to the photoresist. Solvents then are used to remove the areas hit by the UV light, thus creating a patterned mask layer. Areas hit by the UV resist.
Ooh, ooh. It's starting to click. It's starting to click. Let's see. Kind of curious, actually. 1821. Alright, not bad. BFC, SEC filings. Acquired. $15,000 times 16. Right, if I just do 10, that'll be 150,000. 16. Ooh. I can, yeah. So 10 times 50,000. 15,000, 150,000. Plus 6 times 15,000. So it'd be 90,000. 6,000 times 90,000. It's not much. It's like 240,000. 240,000, right?
Solvents then are used. A pattern is applied. Next, using UV light and a stencil spread across the top. Next, using UV light and a stencil.
Very much like this. Top of the photoresist. This protects the underlying material. Being touched by apply light is shown on top. Interconnects layer 2. Unmasked. Resist is affected. Alright, nice.
A pattern is applied to the photoresist. Solvents then are used to remove the air.
Photoresist develop. After step, solvent is used. So what's a solvent? I think a chemical, right? Chemical liquid. Solvent. Liquid is used to wash the photoresist that was exposed to lights, right?
Areas hit by the UV light, thus creating a patterned mask layer. Areas
So this ends up leaving a patterned mask area. The interconnects layer. Okay.
hit by the UV light, thus creating a patterned mask layer.
So the mask layer first, what am I using? Okay.
Using the mask light, thus
Etching.
creating a patterned mask layer. Using the mask, the revealed silicon dioxide is etched away down to the previous layer. Next, the mask layer is removed, and a layer of copper is added to cover the wafer and fill in the areas that were just etched away. Added to cover the wafer, the mask layer is removed, and a layer of copper.
Oh shoot. Okay, so these little pieces right here are also hit by the photoresist. Okay, I didn't realize that. Yeah, that's kind of interesting, right? Right, so this etching thing then removes the... Oh shoot, what is this? The insulating material? Not entirely sure.
Next, the mask layer is removed, and UV light, thus creating a patterned mask layer. Using the mask, the revealed silicon dioxide is etched away down to the previous layer. Next, the mask etched away down to the previous layer.
Yeah, I don't know what this is. So I guess, yeah, does etch mean? So engrave, drawing it. So erode / eat away. Okay. The silicon dioxide material underneath the photoresist portion that is not affected, not covered by the stencil. So this photo etching will go all the way to the next, to the interconnects layer underneath.
Next, the mask layer is removed, and a layer of copper is added to cover the wafer and fill in the areas that were just etched away. Finally, the surface is ground down and leveled off to reveal the copper and insulator patterns, and thus a single layer reveal the finally the and fill in the area, and a layer of.
Okay, so step 6 is going to be the photoresist removal, and step 7 is what is step 7 again? Oh, copper. I don't know. Lay down copper, and then I think it was planar, right?
Next, the mask layer is removed to the previous layer. Next, the mask layer is removed, and a layer of copper is added to cover the wafer.
Silicon etched to underneath it. The remaining resist is solvent.
Is removed, and a layer of copper is added to cover the wafer and fill in the areas that were just etched away.
So this is metal deposition.
Next, the mask layer is removed, and a layer of copper is added to cover the wafer and fill in the areas that were
once the painting photoresist is washed away, copper is filled. Fills the area that was etched. I guess etched away is also appropriate here. Interconnect system. Wire layer. So it's pretty difficult to fit the copper perfectly, so usually it's filled above the etched areas.
just etched away. Finally, the surface is ground down and leveled off to reveal the surface is ground down and leveled off.
Because copper is too step. Yeah, what is a planner? Really never surface. Oh my god, that's crazy. Here, smooth surface feels. Final copper dioxide.
Off to reveal. Finally, the surface is ground down and leveled off to reveal the copper and insulator patterns, and thus a single layer is completed. In order pattern is ground
Oh shoot.
down and leveled. Off to reveal the copper and insulator patterns, and thus a single layer is completed. In order to build the next layer, which is a vertical set of metal vias,
wait, what does he say here? Metal vias. Connection. Okay.
We repeat the same set of steps, but use a different pattern for the photomask. Since these layers are all built using the same set of steps, it's more effective to visualize the set of metal vias.
Build them next. Paste. Set up. Connection for the next layer. Okay.
We repeat the same set of steps, but use a different pattern for the photomask. Since these layers are all built using the same set of steps, it's more effective to visualize the steps as a circle, like a clock. To build all the 80 layers of the die, this sequence is repeated over and over, resulting in 940 steps. One important note is that the FinFET transistors at the bottom are even more complicated than the metal wires, and thus additional steps are needed to fabricate them. Furthermore, cleaning the wafer to wash away dust particles that may have landed on the wafer, as well as inspecting the wafer to make sure everything is being built properly, happens frequently, and these steps need to be added to the circle.
That's tough.
A different tool is used to complete each of these process steps. Now that we have used to complete each of these process steps,
This would be like a more in-depth beginner. Making a microchip cost beginner level. Yeah, that's crazy.
now that we have an understanding of the steps, let's take a look at this semiconductor fabrication plant. This CPU is manufactured on a 300mm silicon wafer, which can fit 230 CPU chips. In contrast, DRAM chips are considerably smaller, and thus 952 of them can fit on a wafer. These silicon wafers are carried in stacks of 25 using a container called a front opening universal pod, or FOUP. This sealed plastic wafer carrier is transported around the cleanroom floor using an overhead transport system which lowers the FOUP onto the tool's landing pad. Inside the tool, robotic arms transport the wafer through vacuum load locks and to different process chambers where materials are added, removed, or processed in ways that we'll explore later. The wafers are then returned to the FOUP, resealed inside, lifted up to the overhead transport system, and carried to and dropped onto the next tool, where the next step in the process is completed. To build the entire chip composed of 80 different layers, it takes 3 months of traveling from tool to tool, where at each stop one of the 940 process steps is completed. In order to increase the microchip mass production capabilities of a semiconductor fabrication plant, or fab, typically there are dozens of the same semiconductor tools organized in rows that perform the same process. On the clean room floor, there are a total of 435 semiconductor tools, resulting in the fab's production capacity of 50,000 wafers, or 11.5 million CPUs a month. These tools have rather complicated names, so we'll start by categorizing them according to their functionality. There are 6 groups: making the mask layer, adding material, removing material, modifying the material, cleaning the wafer, and finally, inspecting the wafer. We've color-coded the different functional groups to the various tools and process steps to help you not get lost.
Bro, this is so good. This is such a good video. Oh my god. Chat. This is making me excited. I don't know why, but there's good music in the video too. Okay, I think I'll be back in a sec. So where do we leave off? Categories of fabrication tools. Okay, so here's my thing. I think I might continue watching some of these videos until 10, and then we gotta move on to the Intel sort of mental model and also financial model as well.
Fabrication plant. This CPU is manufactured on a 300 millimeter silicon wafer, which can
So I guess
fit 200.
notes. Making a microchip. Shoot. Oops. I think I'm going too high. Okay, nice. The fab. So this is the actual fab itself.
130 CPU chips. In contrast, DRAM chips. Take a look at this semiconductor fabrication plant. This CPU is manufactured on a 300 millimeter silicon wafer, which can fit 230 CPU chips. In contrast, DRAM chips are considerably smaller, and thus 952 of them can fit on a wafer. These silicon wafers are carried in stacks of 25 using a container called a front opening universal pod, or FOUP. This sealed plastic wafer carrier is transported around the clean room floor using
Silicon wafers. All right.
chips. In contrast, DRAM chips are considerably smaller, and thus 952 of them can fit on a wafer. These silicon wafers are carried in stacks of 25 using a container called a front opening.
Chips are small. Yeah, that's nice.
Opening universal pod, or FOUP, using a container called a front opening universal pod, or FOUP. This sealed plastic wafer carrier is transported around
Front door opening pod, right?
or FOUP, using a container called a front opening universal pod, or FOUP. This sealed plastic wafer carrier is transported around the clean room floor using an overhead transport system which lowers the FOUP onto the tool's landing pad. Inside the tool, robotic arms or FOUP.
Okay, so carry stacks of silicon wafers. So around the clean room, deposit them to the various machines used throughout the fabrication process. Front open universal, front opening universal pod. Yeah, not too sure what that is. Fab. Semiconductor fab. Yeah, it's these things right there. Oops. Travel above. Actually, it's really smart design. Because then you don't have all of these on the ground. They're just traveling above, so they're unobstructed from anything. Smart idea.
Are all built using the same. This sealed plastic wafer carrier is transported around the clean room floor using an overhead transport system which lowers the FOUP onto the tool's landing pad. Inside the tool, robotic arms transport the wafer through vacuum load locks and to different process chambers where materials are added, removed, or processed in ways that we'll explore later. The wafers are then returned to the FOUP, resealed inside, lifted up to the overhead transport system, and carried to and dropped onto the next tool, where the next step in the process is completed. To build the entire chip composed of 80 different layers, it takes 3 months of traveling from tool to tool, where at each stop one of the 940 process steps is completed. In order to increase the microchip mass production capabilities of a semiconductor fabrication plant, or fab, typically there are dozens of the same semiconductor tools organized in rows.
Cute. Production capabilities. Fab. Right. Increase the production capability of a fab. So stacked row by row. Stacked row by row. Increase the production. Increase the capacity.
Rows that perform the same process.
Perform same process.
On the clean room floor, there are a total of 435 semiconductor tools, resulting in the fab's production capacity of 50,000 wafers or 11.5 million CPUs.
So, I guess some key questions I'm having is like, okay, how many wafers can a fab produce each day slash month slash year? What is the yield on most fabs, right? I guess the yield is, remember how we talked about the analogy of baking a cake? Well, it turns out if any of those steps is fucked up by like 1%, so the degrees at which you bake the cake is 400, but you actually send it to like 404 or 401, and it's gonna fuck up the cake, and all the dyes or chips on the wafer, you can't use them anymore. So I think there is some variability in chip manufacturing, and this causes unusable wafers which is the idea of yield, where how many wafers can you actually use versus how many are destroyed.
A month. These tools have rather complicated names, so we'll start by categorizing them according to their functionality. There are 6 groups: making the mask layer, adding material, removing material, modifying the material, cleaning the wafer, and finally, inspecting the wafer.
Okay, interesting. This is a very good
Material, adding material, removing material, modifying the material, cleaning the wafer, and finally, inspecting the wafer. We've color-coded the different functional groups to the various tools and process steps to help you not get lost. Let's next look at each of these semiconductor tools and see how they process the wafer in various ways. We'll start with the ones that are used to make the mask layer or the nanoscopic stencil on the wafer. These
basic second year CS. Yeah, damn.
Wix gives you the freedom to tell your story.
It's hard to believe that all your photos, videos, and to most of us, it's this marvelous in zeros. You know, because computers work in binding capabilities for your memory cell. The main thing is that only one layer in the string is either written to or read from at any given time. Let's move on in complexity. Most smartphones can store 128 gigabytes.
Okay, let me see.
We have an engineering puzzle for you. Let's set it up. First, here's just one of the hundreds of millions of nanoscopic charge-trap flash memory cells used to store information in your smartphone, computer, tablet, and dozens of other devices. Second, it's composed of 3 functional sections: a gate, a charge trap, and a channel, with dielectric barriers used to separate each section. Third, this memory cell can be used to store 1 bit of information, either a 0 or a 1. Cell can be used to store 1 bit of information, either a 0 or a 1, using electrons in the charge trap. If there are electrons on the charge trap,
How does very curious actually.
73,000 terawatts. That's a lot of solar. The Earth intercepts a lot of solar power, 173,000 terawatts. That's 10,000 times more power than the planet's population uses. So is it possible that one day the world could be completely reliant on solar energy? To answer that question, we first need to examine how solar panels convert solar energy to electrical energy. Solar panels are made up of smaller units called solar cells. The most common solar cells are made from silicon, a semiconductor that is the second most abundant element on Earth.
Huh. So it seems like semiconductors are used, I guess silicon is also used for solar cells. Interesting. Right. Technology. Call this energy. Solar. Solar panels. Solar cells.
Made from silicon, a semiconductor that is the second most abundant element on Earth. In a solar cell, crystalline silicon is sandwiched between conductive layers. Each silicon atom is connected to its neighbors by 4 strong bonds, which keep the electrons in place so no current can flow. Here's the key. Solar cell semiconductors solar to electrical energy. Solar panels are made up of smaller units called solar cells. The most common solar cells are made from silicon, a semiconductor that is the second most abundant element on Earth. Layer on. An N-type silicon has extra electrons, and P-type silicon has extra spaces for electrons, called holes. Where the two types of silicon meet, electrons can wander across the p-n junction, leaving a positive charge on one side and creating negative charge on the other. You can think of light as the flow of tiny particles called photons shooting out from the sun. When one of these photons strikes the silicon cell with enough energy, it can knock an electron from its bond, leaving a hole. The negatively charged electron and location of the positively charged hole are now free to move around.
This kind of reminds me of like photolithography, right? Because you have light that's shining onto something, and this is causing some type of chemical reaction.
But because of the electric field at the p-n junction, they'll only go one way. The electron is drawn to the N side, while the hole is drawn to the P side. The mobile electrons are collected by thin metal fingers at the top of the cell. From there, they flow through an external circuit, doing electrical work like powering a light bulb, before returning through the conductive aluminum sheet on the back. Each silicon cell only puts out half a volt, but you can string them together in modules to get more power. 12 photovoltaic cells are enough to charge a cell phone, while it takes many modules to power an entire house. Electrons are the only moving parts in a solar cell, and they all go back where they came from. There's nothing to get worn out or used up, so solar cells can last for decades. So what's stopping us from being completely reliant on solar power? There are political factors at play, not to mention businesses that lobby to maintain the status quo. But for now, let's focus on the physical and logistical challenges.
A lot like magic. Curious.
You have controls them exactly how you want. That's really cool to me.
Mechatronics deals with how to control mechanical systems. It's a class.
You want components. Cool subsection of engineering. You have these very basic electrical components, and putting them together in a certain configuration controls them exactly how you want. That's really cool to me.
Mechatronics deals with how to control mechanical systems. It's a class that bridges electrical engineering and mechanical engineering through the controls framework.
It's very difficult to learn controls. There's just such a wide breadth as well as a deep depth of content in the field.
To me, there was still a huge gap between what I knew and how to actually apply these concepts, and mechatronics really helped me in closing this gap.
Mechatronics spans what are traditionally separate departments, and the space between typical disciplines is actually a very active and creative space for design.
We had to make measurements and to actually design controllers around these systems that were functional in the actual hardware.
The principles in these labs are often taught in introductory controls classes, but we were able to use them in clever ways.
They realized that simple chalkboard models might be the beginning of an approach, but you have to adapt how you really design things based on expanding a model to cover behaviors that you observe.
In an intro class, you may say, I want to have this heater put out almost infinite amounts of heat to heat up this room. And while that works great on paper, that heater does not have infinite power.
It's easy for myself, and I'm sure many others, to forget the connection that all of the work that we should be doing as mechanical engineers should be able to be applied back in the physical world. That's what we do after all.
My most important objective for this class is that students learn real tools that they will find useful years from now in their own engineering research or practice.
Trumper really emphasizes being able to do like back of the napkin calculations so that you have really strong intuition as to how a system works.
For mechanical engineers, pretty much all real systems have electronics and controls and instrumentation. And so our students really need to know how to work across those boundaries.
The biggest takeaways that I've gotten is how to troubleshoot problems, how to think about ways to tackle them from things that I've experienced.
Being able to see how multiple pieces fit in together and create one whole working system is just really empowering to me as an aspiring engineer.
We're coming up on a major fundraising deadline, and there aren't many more between now and the election. So I am asking you to pitch in right now to help us meet our goal. There is too much at stake, so let's not fall short on our resources. We are working hard to reach voters across the country, but I need you on board to help us win.
Around DRAM, we recommend watching it first at 1.25 times speed, and then a second time at 1.5 speed to fully comprehend this complex technology. Stick around, because this is going to be an incredibly detailed video. Have you ever wondered what's happening inside your computer when you load a program or video game? Well, millions of operations are happening, but perhaps the most common is simply just copying data from a solid-state drive or SSD into dynamic random access memory, or DRAM. An SSD stores all the programs and data for long-term storage, but when your computer wants to use that data, it has to first move the appropriate files into DRAM, which takes time, hence the loading bar. Because your CPU works only with data after it's been moved to DRAM, it's also called working memory or main random access memory, or DRAM.
I'll spend like 7 minutes on this one and then probably gonna stop there. But the reason I want to do this is because as I'm thinking about Intel and pitching it, there's kind of this one-for-one swap I need to make within the portfolio. And right now I think we're holding Micron Technologies, and Micron, they're the one that's producing memory type products. So I think storage, memory, DRAM is one of their specialties, I'd say. So I think that it'll be worth understanding a bit how the thing works underneath the hood.
Simply just copying operations are happening, but perhaps the most
thing here is how do I move this? Oh, nice. Okay. can maybe delete this. Open up. Alright. Go to semiconductors. Yeah, maybe it would be worth putting technologies, memory, logic, right? Manufacturing.
Most common is simply just copying data from a solid-state program or video game? Well, millions of operations are happening. But perhaps the most common is simply just copying data from a solid-state drive or SSD into dynamic random access memory or DRAM.
Fun facts. One of the most common operations computer is doing is copying data from moving from storage SSD into DRAM to memory. So DRAM. Okay.
An SSD stores all the programs and data for long-term storage, but when your computer stores random access from a solid-state drive or SSD into dynamic random access memory or DRAM. An SSD stores all the programs and data for long-term storage, but when your computer wants to use that data, it has to first move the appropriate files into DRAM, which takes time. Hence the loading bar. But when your computer wants to use that data, it has to first move the appropriate files into DRAM, which takes time. Hence the loading bar. Because your CPU works only with data after it's been moved to DRAM, it's also called working memory or main memory.
Okay, memory, I'll go with this. Device used to store data used by the CPU. People refer to this as data stored as working memory, main memory.
The reason why your desktop uses both SSDs and DRAM is because solid-state drives permanently store data in massive 3D arrays composed of 1 trillion or so memory cells, yielding terabytes of storage, whereas DRAM temporarily stores data in 2D arrays composed of billions of tiny capacitor memory cells, yielding gigabytes of working memory. Accessing any section of cells in the massive SSD array whereas DRAM 1 trillion drives permanently store.
Why memory? Core reason why memory storage is separated is because it is slow to fetch data from storage, but fast. Right, so I think the underlying architecture here is the load store architecture. I remember, so I think in class we had talked about this, right? I think what had happened before was, or if you look at the evolution of how memory worked in the past, I think DRAM was kind of like the first sort of invention that kicked off being able to store data. And I think the very first ways that data was stored was just solely on DRAM. You didn't have a SSD or any storage device. I think flash is another thing, flash memory. So you do everything on your DRAM, and it can only store only a few gigabytes, maybe a few megabytes of data. And then that DRAM storage or data capacity grew over time. But I think along the way, new technologies were developed, so you could use a blend of memory, so DRAM, and solid state drive storage, so you could pull in any of the data that you need from storage into your working memory, and then have your CPU just fetch things directly from your DRAM for faster reading and writing. For SSD. Okay.
Store data in massive 3D arrays composed of a trillion or so memory. Store data in massive 3D
SSD.
3D arrays composed of a trillion or so memory cells, yielding terabytes of storage.
Memory. I don't know what a memory cell is.
Whereas DRAM temporarily stores data in 2D arrays composed of billions of tiny capacitor memory cells, yielding gigabytes of working memory. Accessing any section of cells in the massive SSD array and reading or writing.
I guess these are the 2D arrays. Okay. Oops. So DRAM uses 2 data temporarily in 2D arrays. CE lattice below. Yeah, I think lattice refers to the cross.
Writing data takes about 50 microseconds. The array working memory. Billions of tiny capacitor memory cells, yielding gigabytes of working memory.
Capacitor memory cells. So if I remember correctly, a capacitor is something that stores some type of current or signal.
Accessing any section of cells in the massive gigabytes of working memory.
So I think I'm gonna end this one here. Yeah, gonna watch some pretty good videos on memory and also semiconductor fabrication. I'm gonna take a break for a sec, and then I'll get back to maybe Intel. Yeah. You know what? Let's see if we can do the NYT Mini. Webs. Total Wower. Not too sure. Pumpkin Spice Order. Latte. Paperless Party Announcement. An email or Evite. Discourage. Craft. Weave. Oh. Wipe out and faceplant. Eat it. Flat top landform. So starts with a V. Take steer. Teeter. And as colors. No. Heats. Yeah, I'm not too sure what this one is. Beast. Nah, it can't be. Flat top landform. What's free? Let me double check. Okay. So Petter. Shoot. I'm giving up at this point. Better. Ran as colors. So ran like run away. Chalk as colors. Streak. Huh. Bled. Deter. Total Wow. Bird. Butte. Yeah. Butte. Interesting. What about the Wordle? Oh, connections. Yeah. Monticello. I don't know what Monticello is. Sounds familiar though. I think a place in Italy. Let's see, maybe Greek, Monticello, Business, Spark, Arts, Shield Comics. This one's hard. Rings, crown, torch, shield. Business. Oh, maybe things to study. Right, business, arts. Actually, I don't know. Like business, arts, sports, rings, sports, rings, Greek, garden wedge, potato wedge, right? Potato garden, Greek potato, potato words, arts, things you do. Arts, comics, sports, things to do for fun, right? Bark, tree bark, tree roots, tree rings, yeah, things of a tree, right? A crown is a wedge. Let's see. What a way. I feel like that's gotta be comics, arts. I don't know, just a random guess. Newspaper sections. Oh, arts, business, comics, sports. Okay. Chef, Iron Chef, Iron Shield, Iron Garden, Iron Wedge. Let's see, like an iron thing? Fuck. Park, it's a tree garden. Shit. Okay, I don't know. Yeah, what is Monticello? Oh, it's a Thomas Jefferson thing. Eagle, like American things. Yeah, this one is tough. What's this? Oh, tree features, so it is a crown. Okay, nice. What is a tree crown? Okay, so what was... Oh, shoot. I forgot what I selected earlier. That I think it was... Eagle... Monticello, garden... Oh, yeah, because oh yeah, I think it was iron, iron crown, iron shield, iron chef. Iron torch, iron wedge. Iron torch, iron eagle. Yeah. Iron torch, fuck. King of salad. Chef, torch, eagle. What? Kind of salad, chef salad, garden salad, Greek salad, wedge salad. Yeah, that's tough. That's tough. Alright, try my best. Gonna go for a walk. And then I'll come back. see what we can do. Alright, so I think in our Intel model from earlier today, right? I should say maybe in the schedule. So technology, Intel. Yeah, so we talked about start revenue build, start memo draft, company overview. Okay. I think this may be a little too detailed at first. I think it would be helpful to create a simple model, right? Just to get some of the mechanics going. So we can have our income statement. And then our balance sheet, right? Do revenue, do CCG, DC, AI, networking, then other, then COGS, gross margin, guild selling, general, administrative, R&D. I don't know if they capitalize that or not. Should we capitalize it? Yeah, I don't know. R&D. Let's think. What else? I think depreciation, right? So D&A. Let's get us to operating income. Then we'll do non-operating. Let's do interest, right? So interest expense, non-operating expense. So and before interest. Yeah. And then taxes. Net income. I don't know why I'm like. Oops. What did I do? I can make one there. Okay, nice. So selling, journal, administrative, research and development, depreciation, amortization, operating income. Let's start from 2016. This one. Alright. 2016 might be a bit too late, actually. So let's forecast all the way until, yeah, I'll group this to maybe, start from 2014, how about that? Okay, and then I'll group these to pre-COVID era, right? So let's, how do I group them? yeah, I'm gonna Excel. Data. Where's outline? Columns. Okay, yeah, this is nice. Alright, so let's merge this. Over here. Forecast. Right. Right. I should actually maybe put this as white. Yeah, there we go. Okay, so forecast. Alright, so once we have our income statement, maybe we'll take a look at cash flows. Alright, so to net income, appreciation, net working capital, right, and then this will get us to operating cash flow plus cash flow from operations, right? And then we have capital expenditures, cash flow from investing, right? And then maybe, so debt payments, debt issuance, cash flow from financing. Okay. And then our balance sheet. So this could be a pretty simple model for us then, right? All in one. Okay, so balance sheets. Yeah, I like the way that they I think it was this, right? So they had a left border. I think line style was like that. Yeah, I think it was like this. This is cool. Let's merge this. If I do that, but what if I... Oh, that's tough. So, balance sheet, right, let's do cash. Short-term investments. Let's do inventory for now. Accounts receivable. Okay. So inventory, accounts receivable. Let's do that for now. Maybe in other. Right, and then I'll do plant, property, reliability and equipment, and other long-term assets. Alright, and then let's think about liabilities, right? So accounts payable, current portion of long-term debt. Alright. I think that's probably good. So current liabilities, long-term debts, term debt, I guess lease, obligations, long-term liabilities. Okay, and then on the equity side, we have, let's do retained earnings, right? Common shares. Common shares, additional paid in capital, retained earnings, total equity. Alright. Yeah, I think this is probably a good starting point then. Very simple 3 statements. So we have a forecast period of until 2030. I think this is probably where we see the Meteor Lake and a lot of the process technology or manufacturing come back in-house. I remember that was mentioned in the most recent earnings call. Okay. Alright, I should have these numbers. That was from way before net income. Alright. Let me copy. Wait, when did it start from? 2021. So it should really be here. Oops. Yeah, there it is. 2 in millions of dollars. Okay, that's cool. So we gotta crack open Intel's 10K again. Intel 10K. $45 to consolidated statement of operations. Okay. So 2023. Cogs. That's 32. 517. 618. 35209. Okay. So I'm gonna hard code these, yeah. So these are all hard coded, gross profit. Just take our revenues, subtract, right? So R&D restructuring charges, okay. Five, 6, 3, 4, 7, 0, 0, 2, 6, 5, 4, 3, okay. R&D 15, 190, 17, 528, 16, 046, right, so I guess restructuring is a big one. Not terribly big. 2, 6, 2, 6, 2, negative 62. Alright, so operating income. Actually, maybe can add a minus on all of these. Okay. Interest expense. Okay. 629. It's gotten lower. I mean, it's surprising. Six. And then -42. That's interesting, right? Gain losses on equity investments. So 40. Four, 2, 6, 8. 2, 7, 2, 9. So gains. Equity investments. Net. Yeah, take this. Oops. Don't see the stream. Wait a minute. Oh, I can hear myself. Alright. So let's think about this, right? 54228 should flow. Let's get operating income of 93. Nope, that should not be it. 217 62 16046. Oh, okay, it is 93. Alright, 4629. Oh, so they have an interest net. Okay. Interest net. I guess interest gained. Interest paid. That's very nice. They've been running net positive for a while, it seems like. Oh, I guess 2021 they were actually running at a negative, net negative. All right. Yeah. Actually, plus some. Let me see. Show me clean. Allison, if you're watching, show me the bathroom after, huh? I want to see it. I want to see it. I got one viewer. Let's go. Alright. So this is how we're working. This is how we're cooking. Alright, well, provision for benefit from income taxes. Yeah, I don't know what provision for means. Negative 913. Oh yeah, we want to add this. 913249 negative 1835. Alright. Let's go. Okay, so anything we want that is not hard-coded. So this is kind of far actually. Maybe I'll get rid of this. Alright. Alright, let's hard code this one. Alright, so we have seen, let's see. Yeah, revenue has definitely fallen. I want to get the breakdown of the client compute group, data center, and AI. So networking as well. Yeah, maybe I'll use the other as a plug account. $15.5. Right. Yeah, because we're not given super granular information here, so I guess I'm gonna have to. Yeah, we're not given super granular information, so I'm gonna just use this for now. 2021 to 41. Wait a minute. Is this add up? Oh, no. This is 2021. Yeah. Allison, I see you in the chat. I see you in the chat. I've been looking for you. I have been looking for you. Oh my god. Oh my god. What are you doing? What fumes? Yeah, what fumes, huh? Bleach? Yikes. Alright. I didn't realize you'd be bleaching your shit. That's my bad. Yeah. I know you having any dinner, right? I would be hungry too. You want a spreadsheet? The spreadsheet tastes like bleach. You don't want it. You don't want it. You just said you're trying to get away from bleach. Why do you want to eat it? That's kind of confusing me. Okay, so it's close. You're crazy. You're crazy. No, you can't guilt trip me to feeding you the spreadsheet. I'm not gonna turn easily like that. I'm not gonna let you turn me like that. Okay. Actual. crunch the numbers with my teeth. These numbers are uncrunchable. Not with teeth, at least. They're in the billions. You know how many billions you can fit in your teeth? None. None. Internet of Things. What the hell is this? Lower platform, average selling price. Yeah, maybe I'll go to the earlier version, earlier 10K. Thanks for tuning in though, Allison. I appreciate it. Okay, 23,400. We also have I guess I maybe should create like a total. I don't know why I just did that. Okay. Let's see, in like a percent sales growth. Percent. Oops, I don't know what I just did. I removed something here, I think. I don't know what exactly. Full revenue. So yeah, these aren't hard coded, but this is actually all hard coded. Oop, gotta do this. Yeah, there we go. Okay. DC and AI revenue. I got 23. Oh shoot, this was 23,400. Alright. This one's 4,500. Network in Edge. Mobileye. 1. EGX. Serial accelerated computing graphics. Yeah, I guess they probably added that into client compute, I'd assume. Or maybe data center and AI. Alright, net revenue 77,867. Alright. Let's go black. Let's go percent. Alright, and let's do percent growth and percent margin. Don't want this. Yeah, I like percent growth. Percent growth. Okay. jeez. Oh, okay, yeah. I see, I see. But this is a lot, actually. Okay. Total revenue. All right. So yeah, let me maybe. Oh. Top. Oh no, I do not want this line style. Yeah, this is okay. Going back to cleaning. Okay, nice. Thank you, Allison. I appreciate it. Bottom border. Right. Top border. Nice. Selling general administrative. Yeah. Let's see. So research and development was negative.
Huh?
Oh, no, not Siri. So 17, 528. Restructuring. -2. Selling general administrative. Oh, no, I just realized. So I got a negative 13,556 actually. And marketing, general, and administrative, we have 7002 -2. Oh, minus 6180 minus 198. Alright, and then cogs I think is minus 34225. Percent margin, right? Okay, so what if we do yeah, seems reasonable. Seems reasonable. 2866, right? And this one was 43. Six one two 34225 77867. Right, 77867. Oh, negative 34255. That's why. Okay. Nice. And then, okay, so operating income, let me just double check if this lines up. 22. Oh, shoot. Yeah. So 23, 678. That looks good. Percent of net revenue. Okay. Right. So I think this is probably percent growth. Oh, percent. I spelled it wrong again. Growth. Let me take this, just slap it here for now. Make this look pretty. Alright. Divided by revenue. Okay, so yeah, we can see there is this sort of structural decline here. Damn. And EBITs. Alright. I don't know why I'm doing this right now. It's getting distracted by the layout of this. Okay. Oh, right. The grouping thing. That's how to reveal groups. Grouping in Excel. Press Alt Shift plus equal. Oops. Shift equal. Wait, how do I shoot data outline? How do I? Show slash Excel. Control 8. Oh, I see, I see. Okay. Nice. White border. Alright, so taxes, let's actually gain no moss. So gains loss on equity investments. Right. $1904. We have 504. Okay. 5, nice. And then net income, so 4179. Negative. Okay, so that's solid. Let's do percent growth, percent margin. Let's divide this by total revenue. Yep, and then so the margins here are probably pretty shite now. Yeah, like barely earning anything in this quarter. Okay, so that's a problem. Yeah, it's definitely a problem that Intel's facing, the compressing margins here. Alright. Bottom, actually let's line style. Top border, okay. Top, bottom, fill. Okay, so yeah, this one is pretty. Yeah, so we can kind of see here that there is sort of this reason, like it's apparent why Intel is suffering in the stock market right now. They're just not making anything. Shoot. Okay, so bring things over from net income, cash flow from operations. Okay, yeah, so other adjustments. Share-based compensation, restructuring. Okay, so gains. So I guess they were doing mark-to-market sort of accounting here, right? Yeah. purchase of short-term investments. I guess they are a strong purchaser of treasury bills then. Maybe to offset some of the interest payments. Okay, I could see that. Yeah, let me cash flow from investing. Short-term investments. So option, what is it? Option shift. Wait, okay, there we go. So, likely Intel likely finances interest payments through interest earned short-term bills, right? Shoot. Intel likely finances short-term finances interest payments using short-term bills. Okay, yeah. I think that could be the case. Yeah, so what are the other things, right? We have stock-based compensation. So depreciation plus amortization, right? So depreciation and amortization. All right, stock-based compensation, restructuring. Gains or losses on equity investments net. On dice. So net working capital. Change in net working capital, right? Yeah, maybe that's part of the. Maybe they include depreciation, amortization, in selling general administrative or COGS. All right. Getting kind of tired right now. Gotta go use the bathroom too. I think I might end this one soon. Probably will continue this tomorrow. Yeah. Let me see. Okay. Gonna go use the bathroom real quick for now. Man. Okay. I'm back. Yeah, my head's starting to hurt a little bit. I think I gotta go to sleep soon. And then I have a big day ahead of me tomorrow. Okay. Yeah, so I think I'm gonna end this one here. Yeah, gonna end the stream here. I think tomorrow I'll pick up where we left off. Let me take a look at the Intel schedule, right? Ooh. Finish the bathroom? Nice, nice. Data center and AI. Gonna eat and shower. Alright. Yeah. Enjoy your meal. Enjoy the shower. I think I might end in like 5 minutes. Because I just realized store memo, draft company overview, right? Okay. So, yeah, company overview. Okay. So Intel. Alright, so how should I say this? Intel is global designer and manufacturer of semiconductors. for PCs and servers. Yeah, I think that's probably the best. Okay, for PCs and servers. I don't think it has a mobile. No mobile. Double check, but 99% sure. Currently, the company reports under 5 business segments. So 1, client compute group. Client compute group. Data center. And AI. So networking and edge. Networking and edge. Call this Mobileye and Intel Foundry Services. So client compute group basically design, manufacture chips for laptops, desktops, and I think it was what was the last thing? Other, yeah, okay. No other PC types. This is Intel's largest segment. Design and manufacture chips for servers used to host applications, used to host software and AI workloads. All right. I don't know. Servers, host software, and AI workloads. Okay. Laptops, desktops, and other PC types. Was largest segment. Okay, networking and edge. I honestly don't know what this is. I think so. This is manufacture chips for clients. For chip design customers. Yeah. Mobileye, I think. Not sure what this one does. So likely makes Ethernet. Okay, so I think it does make some type of Ethernet type. Actually made some Ethernet type products. And then Mobileye, so Mobileye, they do the chip design and also manufacturing, I think, for the automobile self-driving stuff. Alright, so chip design and manufacturing for self-driving vehicles. I guess you call those like system on a chip type things. So system on a chip, and Mobileye is a publicly traded company right now. Alright. So this is kind of breakdown of... Actually, I think Mobileye, Intel is selling their stake in Mobileye. So at this point, they're probably not... Yeah. Maybe I'll focus on 1, 2, 3, and 5. Might have sold. Double check. Okay. Diligence position in the semis business. This management's growth. Will AI PC be the next big thing? Mental model of cost structure, yeah. So maybe it'll be helpful to go through kind of an overview of each business segment, right? So the client compute group, data center, and AI. I think that's going to be pretty important. So heading client compute group. Right, and then data center and AI. So the plus CCG. Okay, so the CCG is Intel's largest business segment by revenues. Okay, so Intel's CCG is Intel's core business segment. Within this segment, Intel has 2 product lines that it is currently selling. So Core Ultra, and then just Core. State of the art chips with new micro architecture geared towards AI workloads. Yeah, I think. So what is this called? Have to change my sheets and wash your hair? No! Can't you just do that tomorrow? Change your sheets. Again, Lunar Lake. Classic Intel inside. Product that has been staple of Intel's business since the 2000s, right? Just creating CPUs. That makes chips for personal computers, PCs. Yeah, so that makes chips for personal computers, PCs. So if you're using a Windows, a laptop, if you're on the Bloomberg terminal workstation, chances are that workstation is running on an Intel CPU. Every computer needs a CPU. Central processing units. Intel is a dominant player in this space. To run programs. Computer helps execute instructions. Computer run. Is a dominant player in this space. Okay. Data center and AI. DCAI. Is Intel's second biggest segment by revenue, behind CCG. Okay. Segment produces chips that are used in enterprise data centers for running servers, basically powerful computers that meant for websites process data. Host websites process data, transfer data, form calculations, execute instructions, right? Or execute programs, yeah, programs. Servers, chips that are used in enterprise centers. For servers in enterprise data centers, right? Intel has two, so similar to CCG, Intel currently has okay. Nice. Finish your sheets. Yeah, I'll call you. I'm actually probably gonna go walk back, but if you'll call me on my walk back, that would be great. I love you too. I'll see you. Competition. Intel was once a dominant player in this space, but supplying chips for servers. Yeah, I wonder if does Intel make chips for cloud or for on-premise? Two main product lines, right? So Core, Xeon, Gaia. Intel's flagship data server chip. With X amount of cores. Okay, Intel's AI chip for the data center competes with NVIDIA GPUs. Okay. Customers. Competition customers, maybe. Customers. Okay, so I think I'm probably gonna end this one here actually. So I just started this little bit. I think to-dos, income statement, breakdown each segment, balance sheet, cash flow statement. So client compute group, data center, and AI. Maybe network, edge, and IFS. Competitors, customers, geographies, management, alright. Strategy. Finish a small model build. Finish small model build. Start revenue build. Right. Okay, so try to have a model done by Friday. That gives me around 6 days. Okay, maybe that's doable, maybe it's not. I guess I'll have to wait. I'll have to wait and see. Competition, customers. Industry. Yeah, maybe helpful to go through industry, right? Like customers. Okay, okay. Yeah, I'm gonna think about this one. This one's gonna be an interesting memo to write up, but curious to see what's gonna happen. Okay, so I think with that, gonna end the stream here. Thanks for tuning in. This was a fun one. Learned a lot about process manufacturing for semiconductors. That was a pretty cool video by Branch Education that really described, I think, the sequence of 8 steps, and also what are the core components of a CPU, right? You have the underlying transistors, and then kind of like a cake of, what are they called, interconnects, which are just small metal wires that help transfer data around, and you kind of have this interconnect highway of local, intermediate, and global interconnects. And the actual fabrication process itself happens in the clean room. You have these FOUPs, the front opening universal pod, right? That will transfer these silicon wafers that are 300 millimeters that you can put or manufacture about 200 CPU dies. CPU dies are just the chips themselves versus 900 DRAM dies. So DRAM chips are a bit smaller than CPUs, so you can fit about 3 times as much DRAM dies on a 300 millimeter silicon wafer. And I want to say there's around 8 key steps when making the semiconductor actual chip itself. The first one I remember was you have to do some type of oxidation, silicon oxidation on the chip, and then add a layer of photoresist. Once you do that, you then add a stencil, and you do some photolithography to cut out or remove the photoresist that doesn't have that isn't covered by the stencil. And then you go through an etching phase where that underlying silicon dioxide that's been exposed gets etched down all the way to the previous layer of interconnect. And then once that happens, I think what happens is the layer of photoresist that hasn't been washed away by the lithography machine, there's a solvent that cleans that off. Okay. After that, I think copper is added to the little ravines of silicon dioxide that's been etched out, and then it gets filled up. And then finally, the last step is kind of leveling things out and smooth through the wafer planing process, or the wafer planarization. That's what it's called. Okay, so that was that. And then you also have within the semiconductor fabrication plant, the clean room, you have, I think, 6 key sort of machines that are used. I think lithography is one. Probably adding some type of substrate or chemical. Removing the chemical is probably another. And then testing or monitoring is probably another one. That's what I can think of right now. I think on the memory YouTube video we watched, that was helpful understanding, okay, you have memory, you have storage. DRAM is in storage. Sorry, DRAM is memory, SSD is in storage. Storage is built up of an array of these memory cells that can store trillions of memory cells that ends up becoming gigabytes of data. And then you have a DRAM chip that maybe has billions of memory cells, so it can only store a few megabytes of data. But I think the 2D lattice structure that the DRAM has allows it to be able to read and write faster than the storage, the SSD, which has a 3D sort of array structure. Yeah, with that being said, I think we also saw on the Intel side, we were able to build out this schedule, and then also look at the previous 4 years So 2023, 2022, 2021, and 2020. We saw that, okay, client compute group was very strong from 2020 to 2021. Then we saw this industry-wide down cycle. I think it's not just Intel, but also AMD, also NVIDIA too on its graphics processing side, not necessarily its data center side. I think maybe ARM, you could say, is maybe another player that we could look at to see. Okay, so Apple, M1, AMD, ARM, NVIDIA, Ryzen, right? RTX, guess. Chip licensing. So I say instruction set architecture licensing. Lenovo, Asus, HP, Dell. I'd imagine all these guys. Okay. Okay. Yeah. Core Ultra. I think this is probably where I'll end. It's starting to get a bit late, and I still gotta write out my schedule for tomorrow. But this is helpful, and yeah, I think I end this stream here. So thanks for tuning in, and I'll see you guys in the next one. Peace.